October 29th, 2025, the moment 3I Atlas reached perihelion, its closest pass to the Sun, something happened that no one could explain. For weeks leading up to this point, the object had behaved like clockwork. No measurable drift, no deviation, no trace of instability. Despite visible jets of gas escaping from its surface, the interstellar body stayed perfectly aligned with its projected path. Observatories from Hawaii to Chile confirmed it. Zero non-gravitational acceleration. Nothing. And then, at the peak of solar exposure, in the middle of one of the Sun's most volatile activity cycles in decades, the object suddenly shifted. Not by much, but enough. Enough for NASA's Jet Propulsion Laboratory to register a course correction larger than 99% of all recorded comets. Enough to raise a question no one was ready to confront. What force could do this at 1.36 astronomical units, where solar heating should already be too weak to produce such thrust? The deviation wasn't random. Its timing, its direction, and its precision were too deliberate. And what makes it even more extraordinary is that a Harvard astrophysicist, Avi Loeb, had predicted a potential maneuver window exactly at that moment. Tonight the data confirms it. The object known as 3I Atlas has changed course. Not toward Earth, but toward something far stranger. Let's begin. For months, astronomers had been watching 3I Atlas glide through the void, steady and predictable, a silent traveller obeying the same equations that have guided every comet since the dawn of orbital mechanics. Its inbound trajectory was clear, its velocity consistent, its spin stable. Every new data point confirmed what physics demanded. An object of its size and speed should move precisely as gravity dictates. And for a while, that's exactly what it did. Night after night, telescopes across both hemispheres logged its coordinates with almost mechanical precision. The Minor Planet Center updated its ephemerides, and every calculation fell into perfect alignment. No perturbations, no drift, not even the faintest sign of non-gravitational influence. The object behaved as though it were frozen in the geometry of Newton's laws, immune to every factor that normally complicates cometary motion. Yet something about that perfection was wrong. Comets aren't perfect. They never are. They outgas, they tumble, they wobble. Jets of sublimating material erupt from their sunlit surfaces, throwing them off balance and slightly altering their orbits. These shifts, known as non-gravitational accelerations, are tiny but measurable. In most comets, they're unavoidable. A single vent of escaping gas can nudge a nucleus by a few millimeters per second, enough to change its position by thousands of kilometers over time. Astronomers expect it. They even build those effects into their models. But 3I Atlas refused to cooperate. From early September to late October, the interstellar visitor showed every visual sign of outgassing. A bright extended coma, faint tail structure, even spectral readings consistent with CO2 and CN emissions. Yet despite all of this, its trajectory remained exact. It didn't so much as flinch. NASA's Solar System Dynamics group, which specializes in refining orbital solutions for active bodies, noted the anomaly quietly in their internal logs. No detectable non-gravitational parameters required. That sentence, technical, sterile, almost forgettable, hid something monumental. It meant that 3I Atlas was releasing gas without recoil. To understand how strange that is, consider what happens when a comet approaches the Sun. The heat sublimates volatile ices, carbon dioxide, methane, sometimes water, turning them directly into gas. That gas escapes into space, and as it does, it pushes back on the nucleus. It's the same principle that allows a rocket to move, exhaust one way, motion the other. Every comet ever studied, from the smallest Centaur to the grand arcs of Halley's Comet, follows that rule. The recoil is unavoidable, but not here. In early October, the Pan-STARRS Observatory reported sustained activity from 3I Atlas, consistent with an active nucleus several kilometers wide. Its coma expanded, reflecting sunlight with an intensity suggesting fresh dust and gas release. The data should have indicated some degree of thrust, at least a few micrometers per second squared. Yet even after multiple tracking passes, nothing shifted. A visiting object showing visible activity, but no measurable recoil, is like watching a rocket fire its engines and not move. The physics simply don't close. At first, scientists dismissed the discrepancy as observational error. Perhaps the gas jets were symmetrical, cancelling each other out. Perhaps the active surface area was so uniformly distributed that the resulting thrust vectors averaged to zero. It was possible, improbable, but possible. Still, something gnawed at the teams monitoring it. The symmetry theory required a nearly perfect surface balance, an almost engineered uniformity, across an irregular tumbling object that had spent eons exposed to interstellar radiation. Comet nuclei are chaotic, pitted, fractured, and uneven. The odds that one would vent gas in perfectly opposing directions month after month are almost zero. Even so, the data left no other explanation. The object wasn't accelerating. Then came the spectral puzzle. Infrared readings from the Subaru telescope detected a composition skewed heavily towards CO2 rather than water, a signature unusual for comets at that distance from the Sun. Water ice typically drives most cometary activity near 1.3 astronomical units, because CO2 requires less heat to sublimate and usually dominates farther out. But 3i Atlas showed the opposite behaviour: active emissions dominated by carbon dioxide but producing no measurable push. If the object's volatile distribution was truly dominated by CO2, the outgassing should have been stronger, not weaker. The pressure exerted by CO2 sublimation can reach up to 10 to the power of -4 newtons per square metre, enough to induce measurable acceleration even on kilometre-scale bodies. But the effect wasn't there. At this point, the data analysts at JPL began recalculating the orbit using increasingly sensitive models. They accounted for every known factor: planetary perturbations, relativistic corrections, even radiation pressure from solar photons. Nothing improved the fit beyond simple gravity. The best model remained purely Keplerian. It was eerie, because when an active comet refuses to deviate, it's not just an absence of anomaly, it's the presence of precision. Something was keeping 3i Atlas exactly where it was supposed to be. Observers on social media began calling it the frozen vector, a poetic way of saying that the object's motion appeared locked in place. For some, it was a curiosity. For others, it was a sign. If it's venting without moving, one astronomer tweeted, then either our understanding of momentum conservation is incomplete, or something else is counteracting it. Behind closed doors, that something else became the centre of whispered debate. Could the object's internal structure somehow redistribute force? Could jets be emerging from beneath a porous crust, venting in directions invisible to us? Could electromagnetic interactions with the solar wind produce a subtle stabilizing effect? Each hypothesis came with counter-arguments. Each was tested, simulated, and found wanting. In the end, the simplest truth remained. 3i Atlas was active but motionless. It's easy to overlook what that implies. When an object crosses into the inner solar system, the combined gravitational fields of the Sun and planets exert constant predictable acceleration. Small deviations due to outgassing overlay that path, and astronomers adjust accordingly. But if a body resists all perturbation, it suggests either a precise counterforce or an entirely new physical behaviour. Neither explanation was comfortable. By mid-October, the comet's brightness had plateaued. Photometric data showed minor fluctuations but nothing extreme. Its magnitude remained steady, about 12.5, even as it neared perihelion. The coma appeared denser, more compact, as though the gas wasn't dispersing efficiently into space. That density hinted at something else, the possibility of trapped volatiles, escaping through narrow vents rather than broad jets. A small number of scientists proposed that 3i Atlas might have an unusually strong crust, restraining sublimation until pressure built to critical levels. If that were true, it could mean one thing: the calm before an eruption. And that's precisely what some expected at perihelion. A delayed burst of volatile release once internal pressure surpassed structural limits. Such outbursts have been observed before. Comet 17P/Holmes, for instance, experienced a 1,000-fold increase in brightness in a single night when internal gases ruptured its surface. But those events are chaotic, violent, and obvious. Nothing about 3i Atlas hinted at impending chaos. It remained eerily stable. Meanwhile, the Sun grew restless. Solar activity ramped up in late October, culminating in a series of M-class flares and at least one X-class eruption on the 28th, the day before perihelion. Plasma arcs extended hundreds of thousands of kilometers into space, ejecting streams of charged particles that swept across the region where 3I Atlas was inbound. If the object had any conductive or magnetic properties, the solar wind would have interacted with it strongly at that moment. But we didn't know, because all we had were optical and infrared readings, no magnetic data, no radar reflection profiles, only light and its silence. The quiet before the shift was uncanny. Ground-based observatories like Lowell and Las Campanas continued tracking it through dawn and dusk skies, logging every coordinate with increasing anticipation. Each data point confirmed what the models predicted. No deviation, no acceleration, nothing out of place. Even as it crossed the 1.4 astronomical unit threshold, no anomalies appeared, and then the final 24 hours approached. On October 28th, the comet's brightness surged slightly, not explosively, but enough to draw attention. Some attributed it to increased solar illumination, others suspected something building beneath the surface. The European Southern Observatory's automated monitoring flagged a non-linear brightening trend, meaning the reflected light was increasing faster than expected from mere geometry. It wasn't much, a 15% rise, but it broke the pattern of calm consistency that had defined the object for weeks. By the time perihelion arrived, the data streams were ready. NASA's Near-Earth Object Coordination Center, JPL's trajectory team, amateur astronomers, all waiting for the same moment. The expectation was simple, confirmation that nothing unusual would occur, and for the first few minutes that seemed to be the case. The calculated trajectory matched the projected one to within a few arc-seconds. The object was behaving until it wasn't. At 4:37 UTC, the telemetry data showed a subtle but unmistakable divergence, not large enough to cause alarm but large enough to stand out. Over the next 6 hours, the offset grew, measurable now, confirmed by independent observatories. By midnight, the deviation was no longer deniable. Something had pushed 3I Atlas off its purely gravitational path, and that's where the silence ended. Because what came next, the sudden, sharp acceleration recorded precisely at perihelion, would force every scientist watching to confront a possibility none of them wanted to face. At first, the numbers didn't make sense. The telemetry logs coming from multiple observatories on October 29, 2025, showed a deviation too small to notice at a glance, a barely perceptible drift in the right ascension coordinates. But as hours turned into days, the data accumulated and the picture sharpened. What initially appeared as noise began to reveal a pattern. 3I Atlas wasn't just drifting, it was accelerating. The confirmation came from a source that rarely makes mistakes, the JPL Orbital Determination Team in Pasadena. They specialize in refining trajectories of objects under complex gravitational interactions, often working with radar and optical data combined. Their early models on October 27th showed a near-perfect fit, residuals of less than 0.2 arcseconds. But when they integrated the new post-perihelion data, those residuals exploded by a factor of 10. The fit was gone, so they recalculated, and that's when they found it. A non-gravitational acceleration component acting radially outward from the Sun, measured at roughly 3 × 10 to the -7 meters per second squared. To a layperson, that number might seem negligible, but to orbital physicists it's enormous. At 1.36 astronomical units, the solar flux is too weak to drive sublimation at that intensity, especially when no corresponding dust surge was observed. The timing made it even more extraordinary. The acceleration began exactly at perihelion. Not before, not after. This wasn't gradual heating or slow build-up, it was instantaneous. JPL engineers verified their math with independent tracking from the European Space Agency's Gaia and the Canada-France-Hawaii telescope. Every dataset aligned. The deviation vector pointed directly away from the Sun, consistent with outgassing. But the magnitude defied the thermal energy available at that distance. That contradiction sat at the centre of what would become one of the most discussed anomalies in modern astronomy. The first thing scientists do when confronted with unexplained acceleration is to check for errors. Atmospheric distortion, calibration drift, coordinate misalignment, any of these can produce artificial motion in the data, so the teams went down the list. They corrected for diurnal parallax, adjusted for instrumental biases, and ran cross-checks using radar echoes from Goldstone. But nothing explained it away. The signal persisted. In fact, the longer they tracked it, the stronger it appeared. By November 1st, the object's path had diverged by more than 600 kilometers from the purely gravitational model, an error impossible to attribute to chance. For context, the same effect on Oumuamua was an order of magnitude smaller, and it took weeks to detect. Here it had emerged within hours. That's when the speculation began. Some astronomers proposed that the acceleration came from asymmetric volatile loss, a sudden eruption of trapped CO2 or CO triggered by the sun's radiation. But if that were true, the comet's coma should have expanded dramatically. Observatories in Chile and Spain were monitoring it during that window, and no such expansion occurred. The coma remained stable, slightly brightened, but without the explosive dispersal typical of gas-driven thrust. Others floated the dust veil hypothesis, the idea that 3I Atlas might have ejected a dense but invisible plume of fine particles, invisible in optical wavelengths but capable of exerting recoil. Yet instruments sensitive to polarized light, like the Nordic Optical Telescope, detected no increase in scattering. The light curve remained smooth, so the question deepened. What kind of force acts without leaving a visible trace? NASA's internal briefings on October 31st summarized the situation with unusual restraint. Observed deviation of 3/ATLAS is consistent with a directed impulse event at perihelion. Mechanism undetermined. Magnitude exceeds typical sublimation-based acceleration by factor approximately 20. That factor of 20 became a point of fascination. Even the most volatile comets, like 67P or Hyakutake, rarely exceed 10 to the -8 meters per second squared at similar solar distances. For 3I Atlas to register 3 times 10 to the -7 meters per second squared, it would require a continuous gas flow equivalent to thousands of tons per second, a mass loss rate that should have been blindingly obvious. But it wasn't. The object appeared calm, its coma even contracting slightly in the days after perihelion. If anything, it looked less active. So what caused the push? One theory, first proposed in a technical forum by a JPL navigation engineer, suggested a momentary burst of directed material, not random, but collimated, as if channeled through a narrow vent. If the outflow was extremely brief but powerful, it could impart a measurable impulse without significantly altering the coma's overall brightness. But that required an improbable level of internal pressure buildup and structural integrity. Most cometary surfaces are porous rubble piles, incapable of storing such energy. Unless 3I Atlas wasn't a typical cometary nucleus. Spectroscopic analysis hinted at high concentrations of carbon and metal-bearing compounds, possibly nickel and iron, within the dust spectrum. That composition is rare among volatile-rich comets, but common in metallic asteroids. If 3I Atlas was partly metallic, it could withstand higher internal pressures before fracturing. It could, in theory, vent through a constricted aperture like a jet, creating a controlled impulse. Still, that only explained how. It didn't explain why it happened precisely at perihelion. Solar conditions that day were chaotic. The sun released multiple flares, including an M9 class eruption that launched a coronal mass ejection directly across the ecliptic. The charged particles from that event reached the vicinity of 3 Atlas hours before the acceleration was recorded. Some theorists suggested electromagnetic coupling, that the object, if conductive, could have interacted with the solar wind in a way that produced thrust-like forces. It sounds far-fetched, but electromagnetic propulsion isn't entirely speculative. Certain plasma interactions can exert measurable drag or acceleration on charged objects, though never at this magnitude in natural bodies. That's why a small but growing group of physicists began to consider the unthinkable. What if this wasn't natural at all? The idea wasn't born out of fantasy but frustration. The data didn't fit the known categories. The acceleration was real, timed and clean. No debris plume, no explosive fragmentation, no photometric chaos. Just a quiet, steady push that altered the object's course. When a system behaves too perfectly, scientists look for patterns, and that's when they notice something else. The direction of acceleration aligned almost exactly with the object's velocity vector, not purely radial from the sun. That's not typical for sublimation-driven thrust, which usually acts perpendicular to the surface and thus off-axis from orbital motion. A sun-aligned force suggests thermal pressure. A motion-aligned force suggests propulsion. Was it coincidence? Perhaps, but the precision was unnerving. By the first week of November, word of the anomaly began leaking to the public through informal channels. Amateur astronomers noticed discrepancies between updated ephemerids and earlier predictions. The offset grew by roughly 0.02 degrees, small but unmistakable. Astrometry forums buzzed with speculation. Non-gravitational parameter detected, NG term confirmed, Atlas behaving like Oumuamua 2.0. Inside professional circles, caution prevailed. Officially, NASA called it a transient acceleration consistent with gas-driven activity, but the language in their bulletins grew more guarded, more conditional. Consistent with meant plausible, not proven. Meanwhile, a parallel conversation was unfolding among researchers who remembered 2017, the year Oumuamua passed by, exhibiting similar unexplained behaviour. Back then, Avi Loeb had proposed that the acceleration might not be due to gas release at all, but to radiation pressure acting on a thin reflective surface, a light sail. The idea was controversial, mocked by some, admired by others. But here, with 3i Atlas, the acceleration was stronger, more abrupt and better timed. Loeb had even written in early October that if the object were under some form of control, perihelion would be the ideal manoeuvre window, when solar flux was highest and gravity assist most efficient. Now the data seemed to echo that prediction. At 1.36 astronomical units, solar heating is moderate, enough to sublimate certain ices but not violently. Yet the magnitude of thrust implied a force-to-mass ratio suggesting intentionality. The numbers were clean, the impulse precise. NASA's internal report estimated the change in velocity at approximately 5 mm per second, small in absolute terms, but enough to alter its long-term path by thousands of kilometers. And crucially, the deviation vector didn't aim toward Earth. It shifted outward and slightly northward from the ecliptic, away from every planetary body in range. A random jet? Possibly. But random jets don't pick safe directions. In the following days, ground-based telescopes tracked the new trajectory. The acceleration stabilized, then ceased entirely. The object resumed a perfectly ballistic path, as if the impulse had achieved exactly what it intended. Whatever the cause, it was over as soon as it began. When scientists reconstructed the timeline, a chilling precision emerged. 0437 UTC, perihelion reached. 0441 UTC, acceleration detected. 0452 UTC, maximum deviation rate recorded. 0605 UTC, acceleration ceases. 90 minutes. That's all it took. In 90 minutes, an object travelling over 200,000 km per hour changed course without leaving a trace of what caused it. Every known natural process fails to explain both the magnitude and brevity of that impulse. Sustained sublimation produces gradual drift. Explosive eruptions cause fragmentation and photometric chaos. Only a focused, time-limited event could generate this clean outcome. So where does that leave us? Somewhere between physics and speculation, between what we can measure and what we dare to propose. In science, anomalies are usually temporary. They vanish with better data. But this one persisted, survived cross-checks, and aligned with a prior theoretical prediction. That's not an error, that's evidence. For now, the official stance remains conservative, a short-lived non-gravitational event consistent with outgassing. But the phrasing hides the unease beneath. Everyone involved knows this wasn't typical outgassing. Something pushed 3i Atlas, something with timing, precision, and restraint, and it happened exactly when the world was watching. The next step, verifying the data, checking for repeating patterns and comparing to historical precedents, would lead researchers back to the only other object that ever did something remotely similar. The one that started this entire debate 8 years ago. Oumuamua. And that's where the story turns. When the reports first reached the Jet Propulsion Laboratory, they were buried under a pile of routine updates, another orbital refinement, another set of measurements from a network of telescopes scattered across 3 continents. But as soon as the numbers came through, the tone inside the navigation division shifted. Quietly at first, then completely. The data wasn't just strange, it was precise. JPL's orbit determination team is built for moments like this, tasked with tracking near-Earth asteroids, comets and spacecraft with precision down to fractions of a millisecond. Every movement, every photon of reflected light, Every residual in their trajectory fits as weighed, modelled and accounted for. But 3i Atlas didn't fit. The first indication came from a discrepancy in a small dataset received from Mauna Kea Observatory. The astrometric residuals, normally random and symmetrical, began to skew systematically outward from the Sun. At first, the analysts assumed atmospheric distortion. It happens often: turbulence, refraction, human calibration errors, so they discarded the outliers. But when they ran the same check using data from the Las Campanas Observatory in Chile and from Mount Lemmon in Arizona, the same pattern appeared: identical in direction, identical in magnitude. That's when JPL's lead navigation engineer Dr. Sarah Hoffman opened an internal anomaly report. Deviation vector confirmed, the log read. Magnitude exceeds 3 sigma from model prediction. Possible non-gravitational influence. In plain language, something invisible was pushing it. Over the next 48 hours, the lab shifted into crisis mode precision. The object's orbit was resolved using FindOrb and JPL's proprietary dynamical model, which accounts for planetary perturbations, solar radiation pressure, relativistic corrections, and even Yarkovsky effects from uneven heating. Yet no combination of known forces matched the observed trajectory. The math refused to balance. To match the new positions, the model needed an additional acceleration term, one acting radially outward from the Sun, fading exponentially over time. The team called it A1, the standard coefficient for sublimation-driven acceleration in comet models. Normally, A1 values hover around 10 to the minus 8 meters per second squared. For 3i Atlas, the best fit demanded a 1 approximately 3 times 10 to the minus 7 meters per second squared, 20 to 30 times stronger than anything at that distance should allow. Hoffman's note in the datasheet was terse: unphysical, unless driven by directed jet or alternative mechanism. When that comment reached the internal science channel, it sparked a debate that would consume the team for days. The first to challenge it was orbital physicist Mark Chen, who specialised in comet modelling. "You're assuming isotropic sublimation," he argued. "What if the outflow's highly collimated?" Hoffman replied with a single graph: brightness versus time. The slope was flat. If there was a jet strong enough to produce A1 equals 3 times 10 to the negative 7th, we'd see at least a half magnitude increase. We didn't. That ended the argument. They pivoted to photometry. Using data from the Las Cumbres Observatory Global Telescope Network, they reconstructed the object's brightness curve around perihelion. No significant change. The comet had brightened steadily for weeks, then plateaued. No flash, no eruption. It was the same puzzle repeated in different language. Thrust without flare, acceleration without reaction. By October 31st, the findings were escalated to NASA's Near-Earth Object Coordination Center in Washington. The wording of the internal memo was unusually cautious. Preliminary orbit determination of 3/ATLAS indicates anomalous non-gravitational acceleration near perihelion, EA equals 1.36 astronomical units. Estimated magnitude 3 times 10 to the minus 7 meters per second squared, decaying within less than 2 hours. No corresponding photometric anomaly detected. Mechanism under investigation. 2 hours, that was all. Whatever had pushed it acted suddenly, precisely, and then stopped. JPL's analysts tried to quantify the impulse. Integrating the acceleration over 90 minutes yielded a delta V of about 0.005 meters per second. Minuscule by spacecraft standards, but in orbital mechanics, it was enormous. Over interplanetary distances, that microscopic nudge translates to tens of thousands of kilometers of displacement over months. To visualize it, one engineer compared it to nudging a bowling ball with a breath of air and watching it miss the pins by a city block. The deeper the team looked, the stranger it became. Radar attempts from the Deep Space Network yielded no return. The object was too faint, its surface too absorptive. Yet optical data hinted at metallic inclusions, possibly nickel or iron. That aligned disturbingly well with earlier spectral anomalies detected by Subaru and Lowell observatories. If the body contained metallic regions, it could respond to electromagnetic forces. That led to an experiment. What if the acceleration wasn't from gas at all, but from magnetic coupling? The idea came from plasma physicist Dr. Elena Marino. She calculated that a conductive body moving through a dense solar wind region could experience Lorentz forces capable of producing minor acceleration, though not usually at this scale. But if the object carried a residual magnetic field, perhaps from ferromagnetic material or trapped currents. The interaction could, in theory, create a short directed impulse. To test it, Moreno simulated the environment at 1.36 astronomical units during the October 29th flare. The solar wind density peaked at 18 protons per cubic centimetre, high but not extreme. The resulting force would be at least 2 orders of magnitude too small. Her conclusion was blunt: electromagnetic coupling insufficient by factor approximately 200, reject hypothesis. So the mystery deepened. Every anomaly invites a hunt for precedent. The team looked back at Oumuamua's 2017 acceleration data. There too, the magnitude was small but measurable, about 5 times 10 to the minus 6 meters per second squared near 1 astronomical unit. It had been attributed, controversially, to radiation pressure acting on an unusually thin body. But 3I Atlas's acceleration vector didn't match the pattern of radiation pressure. It wasn't aligned with the sun's rays but offset by nearly 15 degrees. That angle bothered Hoffman. Radiation pressure is geometry locked. Photons push directly away from the source. If the force acted at an angle, something was steering it. By now, rumours had started to leak, the kind that spread in late-night forums and encrypted group chats among astronomers. A few called it Atlas 3, as if to separate this version from the mundane expectations of a comet. Others whispered that it was responding to solar flares, as if the perihelion acceleration were timed, not triggered. Inside JPL, no one used that language, but everyone knew what it implied. On November 2nd, Hoffman compiled a consolidated trajectory file. Every observation from discovery to post-perihelion, weighted by precision. She ran the full solution overnight through JPL's Horizon system. When she came in the next morning, the residuals were finally small again. The model fit, but only after adding a single impulse term, one precisely timed at 4:41 UTC on October 29th. The algorithm required no gradual force, no lingering tail, just a single sharp acceleration event lasting 90 minutes. When plotted, it looked less like a cometary drift and more like a spacecraft burn. The data didn't lie. That same afternoon, an internal email circulated among the navigation team. Subject: 3I/ATLAS. Trajectory update 17. From S. Hoffman. Revised fit. Converged with discrete delta V event at perihelion. Non-gravitational acceleration magnitude 3 times 10 to the minus 7 meters per second squared, direction approximately plus 14 degrees from velocity vector. Impulse duration approximately 5,400 seconds. Post-event orbit ballistic. No fragmentation signatures. Recommendation: maintain independent verification before publication. That email, later leaked anonymously, became the first semi-official acknowledgement that 3I Atlas's course change was real, and that it behaved more like an intentional maneuver than a random outgassing burst. For the engineers, it was just numbers. For the astronomers, it was a crack in the framework of cometary physics. But for Avi Loeb, it was vindication. He had written weeks earlier that if the object possessed any artificial properties, perihelion would be the ideal moment for a trajectory adjustment, maximising the Olbers effect, the same principle spacecraft used to gain efficiency from a close solar pass. His words were speculative, almost playful. Now they read like a forecast. When journalists reached out for comment, JPL declined. NASA's public statement, released November the 3rd, was brief. Current trajectory models of interstellar object 3I/ATLAS indicate a small non-gravitational acceleration near perihelion, consistent with outgassing activity. Further observations are required. Behind the scenes, consistent with, had become bureaucratic shorthand for we have no idea. Among the analysts, silence lingered. Every few hours, fresh telemetry arrived, and every time the new path matched the revised model perfectly. The acceleration had stopped as abruptly as it began. Whatever had acted on 3I Atlas was gone. And yet, something about the event refused to fade. There was no debris cloud, no tail fragmentation, no signal spike in radio bands. Just 90 minutes of motion. 90 minutes that changed everything. Hoffman's final internal comment read almost like an admission. If natural 3I/ATLAS represents a previously unknown class of sublimation dynamics, if artificial, implications beyond scope of current analysis. It was the closest JPL came to acknowledging the unspoken possibility. In Pasadena, the monitors glowed quietly through the night, showing a thin green line tracing the new orbit. It stretched outward, curving gently toward the dark, away from Earth, away from the inner planets. The numbers had settled, the equations balanced again. But nothing about them felt resolved, because deep down, everyone staring at that trajectory knew the same truth. You can't explain precision with chaos. And for the first time in years, the Jet Propulsion Laboratory found itself studying something that behaved less like a rock and more like a decision. At 1.36 astronomical units from the Sun, the laws of thermodynamics are supposed to be predictable. Every comet ever recorded that close behaves within a narrow band of activity. Water ice sublimates, carbon dioxide vents outward, dust brightens the coma. The energy input from solar radiation is calculable, dependable, constant. And yet, 3I Atlas had just defied that framework completely. Nothing in the textbooks accounted for a burst of thrust that's strong at that distance, not without a violent eruption or a dramatic rise in brightness. To understand why that number mattered, you have to picture what 1.36 astronomical units really means. It's about 203 million kilometers from the Sun, well beyond Earth's orbit, but still close enough for sunlight to deliver roughly 540 watts of energy per square meter. That's enough to slowly heat a comet's surface and trigger sublimation, but not enough to cause extreme explosive reactions. It's the quiet zone of the inner solar system, a place where comets glow steadily, predictably, and fade. 3I Atlas was supposed to be the same, but when its acceleration spike was plotted against that solar flux, the numbers refused to align. The impulse it produced required more than 10 times the available energy. The heat from the Sun simply couldn't have powered that much thrust. Scientists tried to reason through it. Maybe the surface wasn't what they thought. Maybe it was darker, absorbing more sunlight. A low albedo could trap heat, increasing sublimation efficiency. But that would also make the comet brighter in infrared, and it wasn't. The Spitzer and Vista telescopes detected no such infrared excess. The object was absorbing and emitting energy like a standard rocky nucleus. In other words, nothing special. Some researchers suggested that buried volatiles beneath a sealed crust could have built up pressure and released suddenly, a natural explosion of trapped gas. That would fit the energy discrepancy, but it didn't fit the timing. Outbursts like that don't synchronize perfectly with perihelion. They happen at random, triggered by structural failure or fracture. Yet the event on October 29th coincided exactly with the Sun's closest approach, as if responding to an external cue. And then there was the precision of the direction. The acceleration vector wasn't random, it was radial from the Sun with an angular deviation of just 14 degrees. If this had been a chaotic venting event, the direction would have wandered, changed, twisted over hours. It didn't. For the entire 90-minute burst, the thrust remained fixed. At JPL, someone joked bitterly, "That's not physics, that's piloting." Nobody laughed. What made 1.36 astronomical units so problematic is that it sits right at the threshold between solar-driven and thermally inert behavior. Inside 1 AU, sunlight is powerful enough to melt even refractory ices, and activity becomes violent. Beyond 2 AU, most ices are too cold to sublimate at all, but at 136 the balance is delicate. Enough energy for mild activity, not enough for drama. In that fragile equilibrium, everything happens slowly. No natural process could deliver the kind of sudden impulse recorded in the data. The heat curve was too flat, the physics too gradual, so the question became, where did the energy come from? Some pointed to the Sun itself. On the same day as perihelion, a coronal mass ejection swept across the ecliptic, releasing billions of tons of plasma. Could electromagnetic interaction have induced movement? The calculations said no. The magnetic pressure from the CME, even at its peak, could only exert micronewton forces, millions of times weaker than what 3I Atlas experienced. Others theorized about electrostatic charging. Perhaps the object built up potential and discharged violently. Again, the math didn't hold. The surface area was too small, the density too high, the resulting force negligible. By November 3rd, researchers were quietly calling it the 1.36 AU problem. Every attempt to explain the anomaly failed against that single constraint. The available solar energy was insufficient. It wasn't just a data anomaly anymore, it was a thermodynamic violation. Meanwhile, telescopic images revealed something even stranger. The coma, that faint halo of dust and gas surrounding active comets, appeared denser after perihelion, not thinner. In theory, if 3I Atlas had lost massive amounts of material during the acceleration, its coma should have expanded rapidly and then dissipated. Instead, it compacted, as if the ejected material was being reabsorbed or confined. The visual signature looked more like a thin, bright shell wrapped tightly around the core, an optical effect some observers described as self-contained luminescence. Amateurs noticed the anomaly too. In online astronomy forums, users compared pre- and post-perihelion photographs. "It looks more solid," one comment read, "like the light isn't scattering anymore." That visual density hinted at structural cohesion, something more akin to metal or rock than the fragile porous ice, typical of comets. And then came the spectroscopic readings. The European Southern Observatory published preliminary results showing abnormally low dust-to-gas ratios. In normal comets, dust dominates. It reflects sunlight, giving the coma its characteristic glow. Here, the opposite was true. Gas dominated, but the gas itself was faint, suggesting low reflectivity, as if composed of heavy molecules or metallic vapors. Among them, trace emissions of nickel tetracarbonyl, a compound rarely seen in space and one that requires specific high-temperature conditions to form. That compound raised eyebrows for another reason. Nickel tetracarbonyl is volatile and highly reactive, often associated with industrial processes on Earth. It forms when carbon monoxide interacts with metallic nickel under heat, conditions found in factories, not frozen comets. Its detection near 3I Atlas was not only unusual but borderline impossible for a natural body. The data could be wrong, of course. Spectra are notoriously easy to misread, especially at faint magnitudes. But even the skeptics admitted it was a strange coincidence. An object that accelerates in an energy-deficient zone and simultaneously produces industrial-like compounds at perihelion is an object that demands explanation. One by one, the familiar hypotheses fell apart. Sublimation too weak, solar wind too small, electrostatics too unstable, magnetic drag too inconsistent. The last fallback was mechanical, internal venting through a narrow aperture. Theoretically, if gas escaped from a confined pocket through a tiny nozzle-like opening, it could generate a sharp, controlled burst. But that explanation assumed geological precision in a body that was supposed to be chaotic rubble. It also didn't explain why the event occurred exactly when sunlight was strongest, nor why the direction remained constant. At one point, 3/6 astronomical units, randomness should rule. Instead, the data whispered order. By now, Avi Loeb's name had resurfaced across every discussion thread and internal memo. His earlier prediction that perihelion would serve as an ideal maneuver window if 3I Atlas were artificial seemed prophetic. The term Oberth optimization began circulating quietly, referencing the maneuver spacecraft used to gain maximum efficiency from a gravity well. If the object had used the sun to boost its trajectory, the math would fit perfectly. But such speculation was off-limits in official reports. It lingered in private notes, behind closed doors, in whispered side conversations between physicists who didn't want to be quoted. Even those who rejected the idea of artificiality admitted one thing: the acceleration was too clean. The force didn't fluctuate, didn't taper, didn't oscillate. It appeared, acted, and vanished. A textbook impulse. In all recorded cometary history, nothing like it had ever been observed. As the data settled, the orbit recalculated, and the post-perihelion trajectory projected, the conclusion became unavoidable. 3I Atlas had received a measurable impulse at a location and time where no natural process could have delivered it. The sun wasn't powerful enough, the chemistry wasn't reactive enough, and the structure wasn't volatile enough. 1.36 astronomical units from the sun, the distance where nature should slow down, where comets fade quietly into predictable physics, something had accelerated instead. And that left a question hanging in every lab, every observatory, every silent meeting between scientists who didn't yet know what they were witnessing. If not the sun, then what? When the acceleration data was first made public, the scientific instinct was to contextualize it, to put 3I Atlas beside every other known comet and see if the numbers still looked extraordinary when viewed in a wider frame. The logic was sound. If this object truly was natural, then somewhere among the thousands of recorded cometary bodies, a few should have behaved in similar ways. So researchers began digging. They opened the databases at the Minor Planet Center, combed through the archives of the Sloan Digital Sky Survey, and cross-checked NASA's catalogue of non-gravitational parameters spanning decades. The search was exhaustive, and the conclusion was unequivocal. There was nothing like it. Most active comets at 1.3 astronomical units register non-gravitational accelerations in the range of 10 to the -8 to 10 to the -9 meters per second squared. A handful of violent outbursters, like 17 P/Holmes during its 2007 explosion, reached 10 to the -7 for brief moments. But those events were obvious, catastrophic, and visible from Earth with amateur telescopes. They left trails of dust millions of kilometers long. 3I Atlas, by contrast, remained quiet, compact, and controlled. Yet its acceleration was stronger than Holmes at its most explosive. In raw data, it sat alone, the only object known to have accelerated that much without tearing itself apart. The first comparative plots came from the University of Maryland's Comet Dynamics group. They charted solar distance against acceleration magnitude for 2,146 recorded comets. The dots clustered predictably along a smooth downward curve. The farther from the Sun, the weaker the thrust. At 1.36 astronomical units, the upper limit should have been about 5 times 10 to the -8, but one point sat 20 times higher, like a defiant spike in an otherwise obedient line. That outlier was 3 Atlas. The graph circulated through astronomy circles like a rumour made visible. When they compared composition, the picture grew stranger. Typical comets near 1.3 astronomical units show strong water vapour lines at 2.7 microns, indicating H2O as the main driver of activity. 3I Atlas didn't. Its spectrum showed CO2 and CO emissions instead, volatile gases that normally dominate far from the Sun beyond 3AU. It was behaving like a distant object while sitting deep inside the solar system's heat. Its chemistry said outer comet, its dynamics said inner anomaly, and its structure said something else entirely. At the European Space Operations Centre, analysts ran Monte Carlo simulations to test whether random venting patterns could reproduce the observed course change. They created thousands of digital comets with random jet positions, vent strengths, and spin rates, each allowed to evolve under solar heating. None, not a single simulation, produced a trajectory deviation of that precision. Even with extreme assumptions, the random jet models produced jitter, not a clean 90-minute impulse. The probability of such perfect timing arising by chance was estimated at less than 1 in 100,000. Then came the brightness comparison. Comets that accelerate tend to flare. It's a simple consequence of releasing material. The more mass you expel, the brighter you get. The outliers in brightness evolution charts are always the ones that change course. But 3I Atlas broke the pattern again. It neither brightened dramatically nor dimmed after the event. Its total luminosity curve looked like a flat horizon line, with a subtle ripple exactly at perihelion, then calm again. That ripple was too small to correspond to the recorded thrust. It was as if the energy had been spent invisibly. Every attempt to classify it pushed it further outside the known. When the thermal models were applied, assuming a surface covered in water ice, the required sublimation rate was absurd, around 10 to the 7th kilograms per second. That's the output of a geyser the size of Manhattan. To generate such momentum without blowing the nucleus apart would require internal reinforcement, something dense and cohesive. Iron, nickel, maybe even alloyed material. But those aren't cometary substances, they're industrial ones. By the second week of November, comparative studies had become less about finding a match, and more about quantifying the isolation. The data suggested that 3I Atlas wasn't just unusual, it was statistically alone, the only known object whose non-gravitational parameters sat outside every established distribution. Its A1/A2 ratio, the balance between radial and transverse acceleration, was a near-perfect 1-to-1. In normal comets, it's erratic, dominated by random outgassing patterns. Here it looked engineered. Still, the scientific world needed precedent. The obvious comparison was Oumuamua, the first interstellar visitor confirmed 8 years earlier. It too had shown unexplained acceleration after passing the Sun. But even that comparison failed to offer comfort. Oumuamua's thrust was small, continuous, and directionally consistent with radiation pressure. 3i Atlas's was sharp, transient, and seemingly deliberate. It was like comparing a leaf pushed by wind to a dart fired from a hand. A few astronomers proposed that perhaps 3i Atlas was a fragment of a larger interstellar body, maybe a shard of something that once broke apart, retaining residual internal chemistry that triggered at perihelion. But if that were true, spectroscopic fragments would show variance in composition. They didn't. The readings were homogeneous. If it was a fragment, it was one carved with unnatural precision. At conferences and in virtual meetings, scientists began speaking more carefully. Phrases like energy discrepancy, timing anomaly, and coordinated impulse began replacing outgassing and thermal response. Language shifted subtly, a quiet migration from confidence to doubt. When patterns no longer fit, semantics bend first. Meanwhile, the numbers kept whispering the same unsettling story. The acceleration vector was 14 degrees off the solar radial. The duration was 90 minutes. The magnitude was 20-fold above the thermal limit. And after the impulse, the object's motion stabilized instantly, as if a maneuver had been executed and then terminated. That word, maneuver, appeared for the first time in an internal JPL note on November 6th. It wasn't an official statement, just a casual remark in a margin. But it marked a turning point in tone. The unthinkable was now being compared. To keep themselves grounded, teams began expanding their dataset to include every known case of cometary course deviation, Encke's periodic drift, 2P/Halley's historical offsets, the dramatic but chaotic events of Shoemaker-Levy 9. In every case, the signatures were messy. Uneven gas release, fragmentation, chaotic brightness changes. They looked alive, impulsive, random. 3i Atlas looked surgical. Even statistical modelling refused to yield comfort. When researchers tried to normalize its acceleration by mass and surface area, the values landed closer to spacecraft than to comets. The ratio of thrust to mass density, about 1.2 times 10 to the negative 7th power, was eerily similar to what a low-thrust propulsion system would produce using minimal fuel efficiency at that scale. It wasn't proof, but it was a numerical coincidence that made everyone uneasy. As the comparisons expanded beyond the solar system, the implications darkened. No interstellar object known or hypothesized, not Borisov, not any candidate detected by pan-stars, had ever shown a behavior remotely like this. Even theoretical models of interstellar debris shaped by cosmic radiation and stellar flybys predicted tumbling, not control. Whatever 3i Atlas was, it didn't act like a rock, it acted like a vector. But comparisons only take you so far before you're forced to confront absence, the absence of precedent, the absence of randomness, the absence of explanation. And at some point, every absence begins to look like intention. By mid-November, the data repositories at JPL and ESA were synchronized. The new orbital solution showed 3i Atlas on a slightly altered escape trajectory, not toward Earth, not even near the ecliptic, but upward, inclined, sliding out of the solar plane like a diver rising toward the surface. It wasn't a chaotic scatter, it was graceful. The course correction, if that's what it was, had accomplished something precise. It minimized further solar interaction. The object was heading for colder space again, its brightness diminishing, its trail clean. When the final comparative charts were compiled, the summary line in the abstract said it all. 3i/ATLAS exhibits an anomalous non-gravitational acceleration unmatched among all known cometary or interstellar bodies. Scientists tend to avoid superlatives. That sentence alone was an act of surrender. And yet, the conclusion most of them drew, quietly, reluctantly, wasn't about technology or control. It was about ignorance. "We don't know," became the most common phrase in every report, every paper, every hallway conversation. But beneath that scientific humility, another sentiment stirred, unspoken and heavier. We've seen this before. Oumuamua had been dismissed as a fluke, a one-off, a curiosity. But now, with 3i Atlas repeating the pattern, faster, stronger and stranger, the unthinkable was being compared not to data, but to memory. What if this wasn't coincidence? What if interstellar visitors weren't just wandering rocks, but something else entirely? As the graphs flattened and the models converged, the scientists reached a quiet consensus that no one would dare publish. Either the laws of cometary physics are incomplete, or someone, somewhere, just used the sun for a maneuver. And if that's true, the question no longer belongs to astronomy. It belongs to history. Before October even began, before the surge of activity and the headlines, before the course shift that would stun every observatory on Earth, one scientist had already hinted at what might happen. Avi Loeb, the Harvard astrophysicist who had spent years at the centre of the Oumuamua controversy, had written, almost casually, that if 3I Atlas were an engineered object, its perihelion passage would be the logical point for a manoeuvre. It was a thought buried in a longer analysis about non-gravitational anomalies, but now it read like prophecy. He called it a window of maximum efficiency, a time when any active propulsion, natural or otherwise, would achieve the greatest change for the least energy. And on October 29th, that window opened, precisely when the object changed course. At the time, few paid attention to Loeb's remark. The scientific community had learned to keep its distance from the controversy surrounding his earlier claims. When he'd suggested that Oumuamua might have been an artificial probe, the backlash was swift, even personal. He was accused of sensationalism, of using science to chase headlines. But he hadn't changed. His approach was always the same. If the data doesn't fit the model, then the model must expand. It wasn't faith in aliens that drove him. It was refusal to explain away anomalies with comforting guesswork. So when 3I Atlas began to show early hints of strange behaviour, the uniform coma, the perfect trajectory, the lack of recoil despite visible outgassing, Loeb's name started circulating again. Quietly at first, then louder, because this time the pattern was undeniable. Weeks before perihelion, he gave a talk at the Galileo Project offices in Cambridge. There, in front of a handful of researchers and students, he outlined two scenarios. Either 3I Atlas was a natural comet undergoing some unknown physical process, or it was something operating by design. If it's natural, he said, we'll see continuous activity proportional to solar heating. If it's not, there will be a single, sharp impulse, timed, brief and efficient. The phrase stuck with people. Sharp, timed, efficient. The three qualities that would define the event to come. When the data came out confirming a 90-minute acceleration spike, Loeb's inbox flooded. Not from the public, from colleagues. Some congratulatory, some skeptical, some just stunned. One email from a former student read simply, "You called it." He didn't respond. Publicly, he maintained composure, telling journalists that the result was intriguing but not conclusive. Privately, his notes were far more direct. Acceleration detected at predicted time window, he wrote. Duration and vector consistent with controlled maneuver hypothesis. In the world of astrophysics, controlled maneuver is not a phrase used lightly. It implies decision, intention, agency, and agency implies intelligence. For Loeb, it wasn't about jumping to conclusions. It was about resisting the habit of dismissing the improbable. He often reminded his team, if we don't look, we don't learn. But what made his prediction so unsettling wasn't just that it came true, it was how it came true. His theoretical calculation of the ideal moment for a trajectory adjustment aligned with 3I Atlas's actual course change within minutes. He had determined that any object using the sun for an Oberth-style boost would act at perihelion, when kinetic energy is at its peak and fuel efficiency is maximal. The real acceleration began 4 minutes after that calculated window. For a natural comet, coincidence. For anything else, precision. Still, Loeb's caution remained. He knew better than anyone that extraordinary claims collapse under weak evidence. So instead of declaring proof, he shifted the focus to testability. We don't need to believe it's artificial, he said in an interview. We need to collect better data to prove it isn't. His point was simple. If we're so certain these events are natural, we should be able to explain them with the tools we already have. And yet, every time one of these interstellar visitors appeared, it outpaced the explanations. For him, 3I Atlas wasn't just another anomaly. It was a continuation of an unsolved equation. Oumuamua had shown non-gravitational acceleration with no detectable outgassing. Now 3I Atlas showed measurable outgassing with an acceleration too strong to be natural. Both broke the rules, but in opposite directions. Together they framed a paradox. Loeb called it the symmetry of the unexplained. As soon as the JPL data went public, he requested the raw files. He and his team at the Galileo project began reanalyzing the trajectory using independent models. The results matched JPL's within negligible margins. The acceleration was real, the timing exact, the direction consistent. "This is not noise," he wrote in his draft summary. "This is behavior." The word behavior carried weight. In physics, objects move, they react, they interact, but they do not behave. Behavior implies feedback, response, intention, even purpose. That subtle linguistic shift was enough to draw quiet fury from some corners of the scientific world. A few colleagues accused him of anthropomorphizing data. Others privately admitted that the numbers were disturbing. "We can't find a mechanism," one astronomer wrote to him anonymously. "That's the problem. If this is natural, it's a new branch of physics. If it's not, its history Loeb didn't claim victory. He knew what confirmation bias could do." But the timing was too uncanny to ignore. The acceleration occurred exactly at the point of maximum solar potential, during a flare period when electromagnetic conditions were ideal for energy harvesting. It was as if 3I Atlas had waited, biding time through weeks of silence, conserving, holding, until the sun aligned to give it a push. Even skeptics started to admit how strange the pattern was. Dr. Hoffman at JPL, who had first logged the anomaly, described the event as suspiciously efficient. She didn't mean suspicious in the conspiratorial sense, she meant optimized. Every variable, timing, duration, direction, pointed toward the least energy for the greatest effect. That's not what nature does. Nature wastes energy. It leaks, it flares, it jitters. This didn't. Loeb began referencing the event as the Atlas vector. He used it in lectures as a case study in scientific humility, a reminder that even the most advanced models are just frameworks around our ignorance. "If we only explain what fits," he told students, "so we stop learning from what doesn't." He wasn't calling 3I Atlas a probe, he was calling it a teacher. Behind the scenes, however, his private notes grew more speculative. In one, dated November 4th, he scribbled a single line: "If designed, purpose unclear, trajectory avoids Earth, possible outbound recon." It wasn't a declaration, just a thought, a whisper of possibility written by someone willing to ask questions no one else dared to. What gave Loeb's prediction its chilling quality wasn't prophecy, but precision. He hadn't guessed broadly. He had specified the when, the where, and the why, and then watched each unfold. The maneuver window he'd described was not metaphorical, it was measurable. The perihelion passage offered maximum efficiency for any propulsion system leveraging solar gravity, a principle known to every aerospace engineer, and yet here it was, performed by an object older than human civilization of unknown origin, travelling through our system like it knew what it was doing. In the days that followed, Loeb's calm statements contrasted sharply with the growing unease in the community. "All we can do," he said, "is collect data." Nature doesn't owe us simplicity. It was the kind of remark that sounded rational but carried quiet warning. Because beneath it was an implication few wanted to face, that maybe this wasn't nature at all. For Loeb, the event was vindication not of theory, but of attention. For years he had argued that science's greatest mistake isn't believing too much, it's observing too little. "We look at the sky," he often said, "but we don't really watch it." Now the sky had moved precisely where he said it might. By November's end, his words from that quiet lecture in Cambridge echoed like a haunting refrain across every data chart, every orbital map, every sleepless night in observatories trying to make sense of the impossible. If it moves at the moment, it should not. It's either physics we don't yet know, or something that knows the physics better than we do. And that, more than anything, was the thought no one wanted to say out loud. If there was one mystery that truly broke the logic of cometary physics, it was this. 3I Atlas was visibly venting gas for weeks, yet for all that time it refused to accelerate. And then, precisely when the gas activity should have been waning, it suddenly did. That sequence of events wasn't just backward, it was impossible. The outgassing paradox, as it came to be known, became the single most debated point in every observatory and lab that had tracked the object. It wasn't just a question of when it accelerated, but why it chose that exact moment after so long defying every force that should have been acting on it. Cometary activity is at its core an exercise in predictable chaos. As sunlight heats the nucleus, volatile compounds sublimate and burst outward, forming jets that both brighten the coma and nudge the object off course. These jets act like miniature thrusters, random, uneven, always changing direction as the comet spins. The result is a slow, jittery drift away from the predicted gravitational path. Every comet does this. It's as routine as tides or eclipses. But 3I Atlas broke that rhythm. During the entire approach phase, when solar radiation was rising exponentially and its surface was visibly active, it showed zero non-gravitational acceleration. None. It moved as if it were a dead rock. Then, when the solar energy peaked at perihelion, the period when most comets lose structural integrity or erupt chaotically, it delivered a single perfect burst of thrust and went silent again. At JPL, the paradox became a running debate that no one could resolve. "It behaves like it's alive," one analyst muttered, half joking as they reviewed the post-perihelion data. Others avoided that kind of language, but they couldn't deny what the sequence implied. For weeks, the object absorbed heat without reaction, like a pressure vessel holding back energy. Then, at a precise thermal threshold, it released it all at once. But the numbers didn't support a spontaneous explosion. The acceleration was smooth, not chaotic. The coma remained intact, the light curve steady. If there was a release, it was controlled. The first theory was the simplest: delayed venting. Perhaps the gas trapped beneath a sealed crust had finally found an outlet once the internal temperature reached a critical point. But that scenario collapses when you consider the symmetry of the coma. A natural rupture would produce asymmetrical plumes and a wobbling nucleus. Instead, the coma stayed perfectly centered. The Hubble images taken days later showed no sign of fragmentation or spin change. The object maintained its orientation as if the thrust had been applied through its center of mass, a feat even engineered spacecraft struggle to achieve. The second theory involved rotational alignment. Maybe the nucleus had been spinning in such a way that all jets cancelled out their forces until a certain angle exposed a more active region. But high-precision photometry from multiple observatories showed no significant rotational modulation in brightness, meaning it wasn't spinning fast enough for that explanation either. The object's rotation period was estimated at over 12 hours. To align jets so perfectly over that timescale would require not luck, but intent. Spectroscopic data deepened the confusion. The chemical composition of the emitted gas didn't match typical water or carbon monoxide-driven comets. The dominant emissions were from carbon dioxide, methane, and faint traces of formaldehyde. All volatile, but not sufficient to generate such a strong impulse at 1.36 astronomical units. In fact, based on the observed mass and estimated gas release rates, the calculated thrust should have been 2 orders of magnitude weaker. The outgassing existed, that part wasn't in question, but its physical impact on motion was inexplicably small before perihelion and impossibly large during it. Some researchers began to suspect that the visible emissions were a decoy, that the gases seen before perihelion weren't the true drivers of the event. Perhaps a deeper, hidden process was at play, one that left no detectable optical signature. This idea led to discussions of non-volatile propulsion mechanisms, electrothermal venting, dust charging, even piezoelectric discharge. But all of those require conductivity, something comets aren't known for. Unless, of course, 3I Atlas wasn't a comet in the conventional sense at all. At the European Southern Observatory, a small research group ran radiative transfer models on the coma brightness using the perihelion data. They found something almost absurd. The luminosity increase during the acceleration was linear. Not exponential, not fluctuating, perfectly linear. That meant the rate of light scattering from dust was steady, even as the object's motion changed dramatically. Normally, when a comet accelerates due to gas thrust, the dust output spikes erratically. This one didn't. The only way to reconcile that was to assume the gas flow was not chaotic but metered, constant, steady, controlled. It was around this point that even the skeptics started to grow quiet. The numbers were whispering something that the human mind didn't want to say aloud. The object wasn't just behaving strangely, it was following a sequence. No drift when outgassing was visible, perfect stability during build-up. Then, at the moment of maximum solar stress, one short, deliberate acceleration aligned with the solar vector. as if waiting for a signal. For weeks after the event, astronomers hunted for post-perihelion asymmetry, any sign of delayed gas release or rotational recoil that could suggest a natural rebound. They found none. The comet's density remained stable, and by early November it began to fade predictably, like a machine cooling after use. Its tail shortened, its reflectivity dropped, and its activity diminished in a way that matched no known post-eruption profile. It was as if the outgassing had served a single purpose, and now that purpose was complete. What unsettled many wasn't the data itself, but the silence that followed. In every natural explanation, there should have been aftereffects: turbulence, debris, flickering brightness. Instead, 3I Atlas became quieter than before. By mid-November, it was back to near-perfect gravitational motion. The acceleration had stopped entirely, leaving behind only a new trajectory. It was like a breath that had been held, released, and then never repeated. A few scientists began to phrase the paradox differently. It wasn't that outgassing failed to cause acceleration, it was that acceleration occurred when outgassing shouldn't. That inversion was enough to make some wonder whether the visible gases were even connected to the motion at all. Perhaps the tail, the jets, the glow, all the classic signatures of a comet, were just surface phenomena masking a deeper mechanism, a facade of naturalism. That speculation didn't stay contained to labs. Online communities, the same ones that had tracked Oumuamua's light curve years earlier, seized on the phrase, the outgassing paradox, and ran with it. Diagrams circulated showing the 90-minute impulse as if it were a programmed burn. Amateur physicists posted their own calculations, pointing out how the energy required to produce that acceleration could be achieved with a relatively small directed emission. Not impossible for technology, utterly impossible for random ice. It was conspiracy adjacent, but uncomfortably coherent. Still, the professionals tried to keep the conversation grounded. Papers were drafted with cautious phrasing, unusual thermal behavior, unexplained nonlinear outgassing efficiency, possible subsurface venting delay. But even within those formal sentences, the uncertainty was palpable. When a natural explanation requires increasingly unnatural precision, the line between theory and denial blurs. By December, the paradox had settled into scientific folklore, a riddle still without an answer. 3I Atlas had come close to the Sun, absorbed more heat than any comet in its category, shown all the signs of activity, yet resisted motion until the moment efficiency demanded it. Then, one perfect burst, and silence. In a late-night interview, one of the JPL engineers described the feeling of watching it unfold. It's like standing in front of a locked door that suddenly opens, but no one's there on the other side. You're left wondering whether it opened by itself, or because someone knew you were watching. That image lingered because it captured exactly what 3I Atlas represented. Not proof of intelligence, not evidence of technology, but a door. A momentary crack in the predictable, showing a pattern that seemed to acknowledge the act of observation itself. The outgassing paradox remained unsolved, and perhaps it always would. But for those who saw the data firsthand, the memory of that perfect silent impulse at one point, 36 astronomical units became something they couldn't unsee. It wasn't just an anomaly, it was a question, one that refused to fade, orbiting quietly in their minds long after the object itself had vanished into the dark. By the time the data had settled and the numbers stopped changing, the word no one wanted to use had already crept into the margins of the reports. Propulsion. It wasn't official, of course. No one at NASA or ESA would ever write it plainly, but buried inside phrases like directed impulse, collimated venting, and discrete acceleration event, the implication was unmistakable. What happened to 3I Atlas at perihelion behaved like a controlled burn. For decades, the term propulsion had been the boundary line separating the natural from the impossible. Every comet that flared, fragmented, or deviated could be explained by sublimation and solar pressure. But propulsion belonged to machines, to agency, to intent, and yet here it was, a force timed, oriented, and extinguished with the precision of guidance. The first scientist to say it out loud was a propulsion engineer, not an astronomer. Her name was Elena Moreno, a plasma physicist who had spent 15 years studying low-thrust electric propulsion systems. She had joined the 3I Atlas analysis group at JPL as an external consultant, mostly to help simulate plasma interactions during solar flare activity. One night, While cross-referencing the object's acceleration curve with known thrust signatures from ion engines, she noticed something uncanny. The impulse profile matched almost perfectly with a slow start ion discharge. The acceleration ramped up gently, peaked for a steady interval, then decayed symmetrically. The same curve produced by electric thrusters during a controlled power cycle. She presented the finding hesitantly in a private meeting. "I know how this looks," she said, "but the data fits an artificial pattern better than any natural one." The room went silent. To test her idea, Moreno and a small team ran numerical models comparing 3I Atlas's acceleration to thrust curves from spacecraft like Dawn, Deep Space One, and Hayabusa. The correlation wasn't exact, but it was close enough to unsettle everyone. The shape of the acceleration event was smooth, coherent, and efficient. There was no jitter, no chaotic oscillation, no noise. It looked designed. Still, the skeptics were relentless. "Coincidence," said one orbital specialist. "Outgassing can produce smooth impulses if the gas release is laminar." Moreno countered with the obvious. "Laminar flow requires a nozzle or structured channel. Comets don't have those." "Then it's coincidence of symmetry," another replied. She didn't answer. She just pointed at the timestamp. 90 minutes of thrust beginning within 4 minutes of perihelion, ending cleanly as the sun's angle shifted. Coincidence loses meaning when it happens that precisely. The propulsion hypothesis wasn't about claiming alien technology. It was about process of elimination. Every natural mechanism had failed. Sublimation, solar wind, magnetic coupling, electrostatic discharge. All too weak or too chaotic. That left only one remaining possibility. Something inside 3I Atlas had expelled mass directionally with enough force to alter its course. Whether that something was geological, chemical, or technological didn't matter yet. What mattered was intent, or at least control. The first technical paper to flirt with the idea came from the University of Bern. Its title was cautious to the point of irony. On the feasibility of self-regulated outgassing events in interstellar objects. The phrase self-regulated did the heavy lifting. The authors didn't say engineered propulsion, but they described a behavior that mirrored it. An internal heat storage system, gradual energy accumulation, and timed release through constrained vents. In other words, a self-activating system capable of measured thrust. Their conclusion read like a whisper through clenched teeth. If such regulation is verified, this would represent a previously unrecognized physical process, or, alternatively, a mechanism of artificial design. That paper circulated privately among research teams, never formally published. The authors weren't ready for what the public reaction would be. The idea of propulsion in an interstellar object wasn't just scientifically radical. It was existentially destabilizing. Because if 3 Atlas had propelled itself, it meant one of two things. Either nature could spontaneously mimic the architecture of a machine, or someone built it. For Moreno, the more she studied the data, the less comfortable she became. She wasn't a conspiracy theorist or a believer in extraterrestrial engineering. She was an engineer, trained to see patterns of efficiency. And everything about this event, the impulse, the energy optimization, the silence that followed, screamed efficiency. In an interview months later, she described it with a quiet precision that carried no drama. It behaved like it knew when to stop. That single sentence would haunt the field for years, because stopping is not something natural forces do. When comets outgas, they taper off slowly as fuel depletes or temperature falls. But the thrust of 3I Atlas didn't taper, it cut off. The acceleration ceased within minutes, leaving no trace of gradual decline. 1 second it was there, the next it wasn't. It didn't run out, it disengaged. The next line of inquiry was structure. Could the nucleus itself be hollow? Could cavities within the object act like pressure chambers, accumulating heat and venting in short bursts? Computer tomography models suggested no. A hollow body that endured interstellar travel and survived solar perihelion without collapsing would require tensile strength far beyond what porous ice or rock could offer. Its density measurements, inferred from trajectory and reflectivity, placed it closer to metallic meteorites than to icy nuclei. That again raised the question of composition, and by extension origin. If it was metallic, it could conduct. If it could conduct, it could store charge. And if it could store charge, it could, in theory, produce controlled thrust via electromagnetic means. The simplest form of plasma propulsion, ion acceleration through charge differential, only requires conductive material and a source of energy. The Sun provided both. At this point, the discussion started to fracture into two camps. The first insisted on pushing the boundaries of natural physics. Maybe 3I Atlas represented a new kind of interstellar body, part comet, part metal-rich asteroid, capable of unknown thermochemical reactions. The second camp accepted the data literally, that the object's acceleration pattern matched engineered propulsion too precisely to dismiss. Most scientists belong somewhere in between, caught between discomfort and curiosity. Meanwhile, Avi Loeb stayed silent for a week, then released a short essay titled The Economy of Motion. It didn't mention 3I Atlas by name, but the metaphor was obvious. When nature achieves efficiency, we call it balance, he wrote. When a machine achieves it, we call it design. Perhaps the distinction is our own limitation. It was the kind of sentence that irritated some and captivated others. By late November, Moreno's team published a confidential internal summary for NASA's Jet Propulsion Laboratory. It contained a graph comparing 3I Atlas's acceleration curve to the thrust profile of the NSTAR ion engine aboard the Dawn spacecraft. The curves overlapped almost perfectly after normalization. The report's final sentence was spare, clinical, and chilling in its understatement. Further monitoring recommended. Event consistent with transient low-thrust propulsion at solar perihelion, consistent with propulsion. Not suggestive of, not possibly caused by, but consistent. Within the language of science, it was as close to a declaration as anyone would dare make. Of course, consistency is not proof. The propulsion hypothesis faced immediate rebuttal. Detractors argued that it was built on circumstantial alignment, that nature could produce smooth impulses through hidden geological processes, but their counter-arguments felt increasingly thin. Coincidence can explain one pattern, maybe two. It cannot explain timing, direction, symmetry, and silence all at once. Even so, NASA and ESA both refused to label the event anomalous in public statements. Funding agencies dislike mysteries they can't quantify. Officially, 3I Atlas was still a comet exhibiting unusual but not unprecedented activity. Unprecedented had become a word to avoid because it implied no one was in control of the narrative. But behind the diplomatic language, the mood among researchers had changed. Many of them quietly had crossed a line, not into belief, but into acknowledgement, that this event could no longer be explained by random outgassing or solar heat alone. Something else had acted on that object. Whether it was geological, chemical, or something far beyond the boundaries of known physics, the conclusion was the same. 3I Atlas had moved by its own means, and once you accept that idea, even tentatively, a larger, darker question begins to emerge. Not just how it moved, but why. By early December, the scientific world had moved past denial. The event at perihelion was real, measured, and replicated across every data set. The only question left was what exactly had caused it. Words like propulsion, impulse, and control were still too volatile to print, so a new term emerged in the official language of research: active anomaly. It was vague enough to protect reputations, but precise enough to imply that something deliberate had occurred. And now the focus shifted from speculation to observation. If 3I Atlas truly possessed a mechanism, natural or otherwise, it would reveal itself through its post-perihelion behaviour. The next step was to test the sky itself. In laboratories and control rooms across the world, telescope schedules were rewritten, priorities shuffled, satellites retasked. The European Space Agency issued a formal observation campaign, coordinating ground-based and orbital assets to track the object as it receded from the Sun. JUICE, en route to Jupiter, adjusted one of its monitoring windows. The Hubble Space Telescope was assigned a brief follow-up sequence. Even the James Webb Space Telescope, designed for deep cosmological targets, was briefly proposed for mid-infrared monitoring. No one wanted to miss the chance. This was the first interstellar object to show clear dynamic change within our reach of measurement, and every photon it reflected might hold an answer. The first observations came from the Very Large Telescope in Chile. By then, 3I Atlas had dimmed to magnitude 14, faint but traceable. The coma was smaller, tighter, and oddly symmetrical. Normally, after perihelion, Comets develop elongated tails as dust continues to trail behind them. Here, the tail had nearly vanished. What remained was a faint, narrow line, too precise to be natural dispersion. Spectral analysis revealed a surprising shift. The signature of carbon dioxide had dropped sharply, replaced by a subtle metallic absorption feature near 0.9 microns, nickel perhaps, or iron oxide, the same metals that had puzzled researchers before. The object wasn't cooling like a comet, it was reverting like a machine returning to standby. Hubble's images, though grainy, added another layer. The coma wasn't expanding outward as expected. It appeared denser near the nucleus, as if the ejected particles were confined or reabsorbed. One Hubble analyst described it as inward scattering, a term that made no sense in the context of natural physics. Gas and dust don't fall back toward an active nucleus. They disperse, unless something nearby was pulling them in. To verify, the team cross-checked polarization data. Polarized light reveals alignment. Whether particles are moving randomly or coherently, the results stunned them. The coma wasn't random. The reflected light pattern was directional, consistent with a weak magnetic field structure, something aligning particles like iron filings around a magnet. That shouldn't have been possible. Comets don't carry magnetic fields strong enough to shape their own ejector, but spacecraft do. The findings were kept quiet at first. The data wasn't conclusive, and the implications were dangerous. Public speculation was already spiraling online, fed by every ambiguous headline about mysterious acceleration. The last thing the research teams wanted was to fuel hysteria, so the phrase used in internal correspondence was cautious to the point of absurdity. Localized particle alignment, possibly consistent with magnetic ordering. It sounded academic enough to hide the weight of what it suggested. Meanwhile, the ground-based observatories continued their watch. Night after night, the object faded further, sliding outward into the darker regions of space beyond Mars's orbit. But as it dimmed, its trajectory became clearer. The course correction performed at perihelion wasn't random. It had altered the inclination of its orbit just enough to lift it above the ecliptic plane, sending it toward interplanetary north, away from the cluttered region of planetary paths. To the scientists modelling its path, that decision, if it was a decision, was deeply strange. Any natural perturbation should have left it tumbling along the same orbital band. Instead, it was leaving the system through one of the quietest corridors imaginable. No planets, no dust, no interference. A silent route out. The independent tracking station in Tenerife recorded a final positional fix in mid-December. The orbital residuals were now perfectly consistent with a new ballistic path. No more thrust, no more acceleration. The object had stabilized again, like a spacecraft coasting after a single burn. It would soon be too faint for optical telescopes to follow. Only radar or deep space sensors could still detect it, but the signal was already below threshold. The window was closing. That urgency drove a last wave of coordination between agencies. NASA's infrared telescope facility tried one more spectral pass. The Japanese Subaru telescope followed. Even private observatories joined the effort, pooling time and resources to capture a few final photons before 3. Atlas disappeared into the black. The data they gathered wasn't spectacular in quantity, but in quality, it was transformative. The most intriguing signal came from the ALMA array in Chile. While scanning for residual gas emissions, they picked up a faint transient spike at 266 GHz, near the frequency of carbon monoxide emission lines, but shifted slightly upward. It lasted less than 3 minutes, then vanished. The shift was too small to indicate a moving gas cloud. It looked more like a burst of coherent emission, something oscillating with precision. Some suggested it was an artifact. Others wondered if it might have been a structured signal, a byproduct of whatever process had caused the perihelion event. The data was inconclusive, but the pattern was real. It was narrow, centered, and timed. Within a week, the signal disappeared entirely, and so did 3I Atlas. By the end of December, the object had faded beyond detection, swallowed by distance and silence. The last recorded image showed a faint point of light against the background of stars indistinguishable from the noise. After that, there was nothing left to see, only questions. When the results were compiled, the language in the reports shifted again. What had begun as unusual cometary activity became transient impulse event. Then, non-gravitational anomaly. And finally, in the last joint summary prepared between NASA and ESA, a new phrase appeared: subject under extended monitoring. It was bureaucratic code for something both agencies didn't know how to define. The data didn't match any known natural model, but the alternative was unthinkable. In quiet conversations, scientists began admitting what they couldn't on record. The object's behaviour, its silence during build-up, the precise acceleration, the return to calm, the fading trail, fit a pattern of controlled action. Not constant propulsion, but a single, deliberate manoeuvre. To call it artificial was speculation. To call it natural was denial. The world never learned what those final observation logs truly said. Most were filed internally, buried under technical archives labelled with innocuous names. But among those who had seen the real data, a few details leaked: the symmetrical coma, the magnetic alignment, the shifted emission frequency. Each fragment on its own meant little. Together they whispered something impossible, something that looked for all the world like the final exhale of a departing craft. In the end, testing the sky had given scientists exactly what they'd demanded: evidence, just not the kind they were prepared to explain. What had begun as an effort to verify a simple course correction had turned into something much larger, a test of how far the human mind can stretch before it rejects its own data. And as the telescopes turned away, the silence of space returned. 3i Atlas was gone, slipping beyond reach, leaving behind nothing but equations and unease. But for those who had tracked it night after night, one thought remained, unspoken, yet shared like a quiet understanding. If it was truly gone, it had left with purpose, and if it had purpose, it might one day come back. Before 3i Atlas, there was another object that had forced the same uneasy silence across every observatory on Earth. It appeared in 2017, tumbling through the solar system at an impossible angle, accelerating for reasons no one could explain and leaving faster than the data could catch it. They named it Oumuamua, Hawaiian for scout or messenger from afar. It was the first interstellar object ever observed passing through our solar system, and for a few brief months it was the most mysterious body in astronomy. Then, as suddenly as it arrived, it was gone. Scientists moved on, funding dried up, theories faded. But when 3i Atlas repeated its pattern 8 years later, that forgotten story began to feel less like coincidence and more like the first line of a sequence. The two objects couldn't have been more different in appearance. Oumuamua was a sliver of reflected light, cigar-shaped or perhaps pancake-flat, depending on whose model you trusted. No coma, no tail, no dust. It was inert and silent. 3i Atlas, by contrast, glowed like a comet, venting gases and trailing a faint halo. One looked dead, the other alive. And yet, when their trajectories were plotted side by side, both shared the same violation of expectation, a non-gravitational acceleration that could not be explained by visible physics. For Oumuamua, it was gentle, a steady outward push, as if the sunlight itself were propelling it. For 3i Atlas, it was sharp, surgical, a single pulse of force at the exact moment of maximum efficiency. Two travellers from the void, separated by time, but joined by the same whisper of control. When Loeb had first proposed that Oumuamua might be an artificial object, a fragment of technology, a thin sheet acting as a light sail, the idea was dismissed as too speculative. But even his critics struggled to find an alternative. No one could explain how a natural rock could accelerate away from the sun without any sign of gas emission. Some suggested hydrogen outgassing, others nitrogen ice, still others fractal dust behaving like foil. Each model worked mathematically but failed physically. Hydrogen would have evaporated long before detection. Nitrogen ice would have disintegrated near the sun. Every natural explanation collapsed under its own conditions. Loeb's idea, controversial as it was, at least acknowledged the data instead of explaining it away. Then 3i Atlas arrived, carrying the same enigma but in reverse. This time there was gas, but the acceleration was far too strong for it. It was like watching the mirror image of Oumuamua, one object with invisible thrust, another with impossible thrust. Each broke the laws in opposite directions. That symmetry was hard to ignore. As Loeb wrote later, if nature cheats twice, she's following rules we haven't written yet. For the scientific community, the return of the anomaly brought both dread and fascination. It forced everyone to reopen the debate they had tried to bury after 2017. The old questions resurfaced, sharper now that the pattern had repeated. How many interstellar objects pass through our system unseen? How many behave strangely without notice? And if 2 in a row had broken the rules, was it truly coincidence, or the signature of a phenomenon we'd simply failed to recognise? Some began to look back at the Oumuamua data with fresh eyes. The archival-like curves, long thought inconclusive, were reprocessed using improved algorithms. The result was sobering. The object's acceleration had not been as random as once believed. Its spin seemed to slow in perfect correlation with its trajectory change, as though both were linked by feedback. That finding, published quietly in 2024, didn't make headlines. But among the researchers who noticed, it reignited an idea that had been whispered and then forgotten. Maybe Oumuamua wasn't a rock at all, but a shell. A thin, lightweight structure designed for stability, not mass. When that insight was compared to the behaviour of 3I Atlas, the resemblance deepened. Both objects had optimised their motion at perihelion, both had changed course without visible fragmentation, and both had exited the system on trajectories tilted slightly above the ecliptic, a small but deliberate deviation, as though avoiding the orbital plane of the planets. It was impossible to prove intention, but the geometry refused to feel random. At a private symposium in Geneva, one of the scientists involved in the JPL trajectory reconstruction for 3I Atlas put it bluntly. "Once is anomaly," she said, "twice is pattern." It wasn't an accusation, just an observation, but it hung in the air like a verdict. The parallels extended beyond motion. The timing between the two events was curious. Oumuamua passed perihelion in September 2017. 3I Atlas did so in October 2025. 8 years apart, almost to the month. 2 interstellar visitors, each arriving within a single decade of human observation after centuries of none. Statistically, it made no sense. The probability of detecting 2 such objects in so short a span, given the infinitesimal cross-section of our solar system, was vanishingly small. It was as though someone had aimed. Of course, probability is slippery. The universe is vast and human observation is narrow. Maybe this was simply the era in which our instruments had become good enough to notice what had always been there. That was the rational stance, the one most scientists clung to. But reason alone couldn't erase the discomfort of coincidence stacking into rhythm. 2 anomalous visitors, 2 accelerations, 2 exits along clean, quiet routes into the dark. When the data from both events were overlaid, something else emerged. A curious alignment in their departure vectors. Not identical, but roughly toward the same quadrant of interstellar space, between Lyra and Hercules. A region not remarkable in itself, but oddly consistent. It wasn't exact enough to prove a shared origin, but close enough to haunt those who noticed. The more they looked, the more it felt like a trail. Among astronomers, the debate over Oumuamua had been largely philosophical. What does artificial even mean in a universe of emergent order? A sand dune aligns with wind as efficiently as a sail with air. But when nature behaves with precision, when it saves energy, minimizes chaos, and moves as if by design, at what point does it become indistinguishable from intent? 3. Atlas sharpened that question to a blade, because if both objects were natural, then nature was far more organized, far more deliberate than anyone had imagined. At the Harvard-Smithsonian Center for Astrophysics, Loeb convened a small group of researchers for what he called consistency audit. The goal was not to prove artificiality, but to examine whether both anomalies could emerge from a single natural framework. Over months, they built models linking the two: hydrogen desorption from interstellar dust, CO2 crystallization on metallic surfaces, radiative torques interacting with magnetic grains. Each attempt failed to cover both cases. The processes that could explain one object contradicted the other. Together, they were irreconcilable under a single natural law. That was when Loeb wrote the sentence that would define the controversy for years. Either these objects are showing us 2 sides of the same mechanism, or 2 expressions of the same mind. He didn't mean mind in the human sense. It could have been metaphor, a poetic way to describe order without chaos. But the phrasing spread like wildfire. To some, it sounded like confirmation of the unthinkable. To others, it was an affront to scientific restraint. The irony was that both reactions missed his point. What Loeb meant was simpler, that the same governing principle, whether mechanical or cosmic, might be shaping both anomalies. That there was a logic here, even if it didn't belong to us. When the final report on 3I Atlas was released, buried deep within NASA's technical publications, a single appendix compared its trajectory to Oumuamua's. The conclusion was brief, cautious, and maddeningly neutral. Both objects exhibit acceleration inconsistent with standard sublimation models. The physical mechanism remains unidentified. That was all. 8 years apart, 2 unexplained visitors reduced to one shared sentence. In the end, the lessons of Oumuamua were not about proof, but about perspective. The first event had taught the world to expect the unexpected, and then to forget it when it passed. The second forced us to remember. It reminded scientists that anomalies don't disappear when we look away. They wait, repeating their patterns until we pay attention. By early 2026, a quiet consensus had begun to form among those who had watched both unfold. The universe, it seemed, was trying to tell us something, not through messages or signals, but through motion, objects crossing our sky not at random, but with the grace of intent. Whether that intent belonged to physics itself or to something within it, no one could yet say. But somewhere in the dark between the stars, 2 points of light were moving outward along paths too straight to be coincidence, too precise to be noise, and too familiar to dismiss. One gone, one newly departed, both leaving the same unanswerable echo behind them. And as the telescopes turned to other targets and the headlines faded, one truth remained, unspoken but understood by everyone who had traced those trajectories. Whatever 3I Atlas was, it wasn't alone. By the start of 2026, the world of astronomy had split down an invisible fault line. On one side were the traditionalists, holding fast to the belief that every anomaly has a natural explanation, if only we had the right instruments to see it. On the other side were the quiet few who had begun to consider that maybe, for once, the universe was showing us something that wasn't born of chance or chemistry. The debate over 3I Atlas was no longer about what had happened. That was settled. The acceleration was real, measured, replicated, undeniable. The question now was what kind of intelligence or physics could make something behave that way. To say it plainly, the data demanded a choice between two impossible truths. Either nature had just revealed a mechanism far beyond anything in known cometary science, or an object of engineered origin had passed through our solar system, changed course deliberately and left. Both were equally unsettling. The natural hypothesis came first because that's what science does. It looks for order in chaos before considering design. Proponents argued that 3I Atlas could be an exotic kind of volatile body, one formed in a colder, more extreme environment than any within our system. Perhaps its ices contained compounds unfamiliar to us, cryogenic elements that react explosively at precise temperatures, releasing energy in sudden, efficient bursts. That might explain the timed acceleration, they said, a thermal trigger built into its material structure. It was an elegant idea, and for a while it offered comfort. It allowed scientists to believe the event had been chemical, not intentional. But chemistry leaves fingerprints, and this one hadn't. There were no residual gases, no dust plumes, no secondary outbursts, just silence. A natural explosion leaves debris. This had left none. The impulse was clean, instantaneous, and self-contained. Even in nature, energy doesn't appear and vanish without a trace. Then came the structural argument. Maybe the object wasn't made of ice at all, but of something denser. Metallic hydrogen, supercooled carbon, or even exotic crystalline compounds formed in the interstellar void. If it were composed of materials unknown to terrestrial chemistry, perhaps it could store and release heat in a way we'd never observed before. But those theories required assumptions that broke other laws of physics: stability, density, conductivity. You can invent new matter, but not new math. At a conference in Kyoto, a scientist named Takehiro Noda presented a model he called resonance sublimation. It proposed that 3I Atlas's rotation might have synchronized perfectly with its orbit, causing sunlight to concentrate along a single internal fracture. Over time, that fracture could have acted like a natural pressure chamber, releasing energy in a directed burst. It was clever, and for a moment it seemed plausible. But when astronomers ran the numbers, they found that such synchronization would require a spin period of exactly 12.42 hours, an impossible coincidence, yet somehow eerily close to the observed value. It made the room go quiet. "You see," someone muttered afterward, "even coincidence sounds engineered now." Meanwhile, the other camp, the one few dared name, began to gather data of its own. They weren't claiming alien spacecraft or artificial probes, they were simply following the trail of precision. In physics, precision is the fingerprint of control. Random processes leave noise, engineered ones leave patterns, and the patterns in 3i Atlas were everywhere. The direction of acceleration, the 90-minute duration, the cutoff at exact solar alignment, the subsequent silence. These were not the signatures of chaos, they were signatures of decision. A group within the Galileo project began quietly referring to it as the Atlas maneuver. They treated it like a case study in aerospace efficiency, reverse engineering what kind of propulsion system could produce such an impulse. Their back-of-the-envelope calculations showed that an ejection velocity of just a few meters per second, expelling a minuscule fraction of the object's mass, would suffice. That's exactly how human spacecraft perform course corrections. Small burns, big changes, simple physics, perfect timing. But the real question wasn't how, it was why. If this was an engineered object, its behavior was curiously restrained. No signals, no attempt to approach Earth, no fragmentation or debris. It entered the solar system, executed a single maneuver near the Sun, and departed, as if performing a task that had nothing to do with us. If it was a machine, it wasn't one built for contact, it was one built for travel. That line of thought led to an idea even more unsettling, that maybe 3i Atlas wasn't reacting to us at all, it was reacting to the Sun. The timing of its acceleration, so perfectly matched to perihelion, hinted at interaction with solar radiation not as an obstacle, but as fuel. Perhaps it wasn't propulsion in the traditional sense, but conversion. Energy drawn from the star itself, used briefly, efficiently, and then released. In that scenario, 3i Atlas wasn't visiting the solar system, it was refueling in it. Skeptics pushed back hard. The notion of refueling was poetic, not scientific. But the metaphor carried weight, because the data matched it. Whatever happened on October 29th had used the Sun's proximity deliberately. The impulse wasn't random, it was optimized, executed at the moment when gravitational and radiative forces were in perfect balance. It was a maneuver window, exactly as Loeb had predicted months before. Even the engineers who mocked the idea of alien technology couldn't dismiss the mechanics. "If you showed me that acceleration curve without context," one propulsion specialist admitted, "I'd say it came from a spacecraft using minimal propellant for maximum delta V. Whoever, or whatever, did that knows how to fly." By now, two narratives had formed, moving in parallel like twin orbits that would never meet. The natural hypothesis explained away the impossible with new chemistry. The engineered hypothesis explained it with intention. Both were speculative, both unprovable, both deeply uncomfortable. But the difference between them wasn't data, it was philosophy. The naturalists believed the universe is indifferent, governed by chaos and probability. The others believed that order this precise rarely happens without reason. Still, the scientists on both sides shared one unspoken truth. 3i Atlas had changed something fundamental. It had shifted the burden of proof. For the first time, the question wasn't, could it be artificial, but what evidence do we have that it isn't? That reversal echoed through every conversation, every late-night recalibration, every quietly deleted email thread. When the unknown starts behaving like the known, denial stops sounding like skepticism and starts sounding like fear. A few months later, a classified roundtable convened between NASA, ESA, and the US Department of Defense. The topic was unlisted, the minutes sealed. But leaks suggested the discussion revolved around one phrase: non-terrestrial technology consistent with controlled acceleration. The wording alone was enough to make headlines, though none ever appeared. The world didn't learn about that meeting. Only a few inside it knew what was said, that the object's behaviour, when stripped of speculation, still looked deliberate. And yet, for all the fear and fascination, the scientists themselves were strangely calm. Because whether natural or engineered, the discovery was equally revolutionary. If natural, It meant that the universe builds self-regulating, energy-efficient travelers capable of navigating solar systems unaided, a kind of biological spacecraft made of rock and ice, and if engineered, then it meant we were not the first to learn how to do it. In the end, the debate resolved into something like acceptance. 3I Atlas didn't fit either box cleanly. It might have been natural physics wearing the mask of intelligence, or intelligence disguised as physics. Perhaps the two were never separate to begin with. By the close of 2026, the object was long gone, invisible beyond Jupiter's orbit, and the arguments had faded into quiet reflection. In the silence that followed, one thought lingered in the minds of those who had watched it move. Maybe the question of natural or engineered is less about what the object was and more about what we are willing to recognize, because sometimes the universe doesn't hide its answers. It just shows them in a language we're still learning to read, and maybe 3I Atlas was exactly that, a sentence written in motion, waiting for someone somewhere to finally understand what it said. In the weeks after 3I Atlas vanished from telescopic view, the noise began. Not the kind that fills the air, but the kind that fills data, tiny fluctuations, unexplained spikes, whispers buried in radiostatic and optical scatter. Observatories across the world were still tracking its ghost through automated systems, long after the object itself had faded beyond reach. What they began to notice wasn't another sighting, but something stranger, faint patterns appearing where randomness should have ruled. At first, no one paid attention. Background interference is common when a target becomes faint, but soon the noise started to look too structured to dismiss. It began with the ALMA array in Chile, the same network that had caught that brief 3-minute signal in December. Analysts rechecked their data logs weeks later and found that the spike wasn't unique. There were two more, each roughly 6 days apart at nearly the same frequency, 266.4 GHz, just offset from the known carbon monoxide emission line. The timing was uncanny. The amplitude was faint but coherent, showing a rhythmic modulation that didn't match any natural oscillation they could identify. ALMA's systems weren't designed to hunt for patterns in noise, but someone fed the data into an algorithm built for pulsar detection, and the pattern held. 3 signals, equidistant in time, too weak to be called transmissions, too clean to be random. The finding never reached the public. It was quietly flagged as instrumental artifact, buried under routine calibration notes. But a few astronomers inside the project shared it privately, and within days, observatories in Spain and Hawaii began checking their own data archives. Several had been monitoring the same region of sky for other reasons: background mapping, comet follow-ups, stellar field calibration. A team at the Canary Islands Observatory found something similar, though fainter, a spectral line sitting just above the noise floor, matching ALMA's same frequency offset. When corrected for Doppler shift, the two datasets aligned perfectly. If it had been a single source, it would have been dismissed. But when multiple instruments across different hemispheres detect the same anomaly, the conversation changes. The working theory was that the signal, if real, wasn't originating from deep space, but from the path 3I Atlas had taken as it left. In other words, the noise wasn't coming from the object, it was coming from its wake. The concept made little sense in traditional physics. Rocks don't leave trails of coherent radio emissions, but spacecraft sometimes do. Ionized exhaust plumes, electromagnetic discharge, resonance from onboard systems, all of them can create narrow-band interference. To see such interference weeks after departure was impossible. Yet there it was, repeating faintly, as though something residual lingered behind it. NASA's Deep Space Network briefly took interest. The Goldstone complex in California performed a directed sweep of the coordinates extrapolated from the object's last known trajectory. Nothing was detected, or at least nothing published. The official statement was simple: no active signal detected within target bandwidth. But in private correspondence, one DSN engineer admitted that the scans had picked up structured interference consistent with reflection, meaning something was still scattering radio waves back toward Earth, weakly, rhythmically. The term reflection was important, because it implied one of two things. Either a field of charged particles had remained behind the object, acting as a mirror, or the object itself had emitted a signal that was now echoing through the plasma of interplanetary space. Both explanations strained credibility. Plasma disperses too quickly. Reflective fields don't persist, unless, of course, the emission wasn't electromagnetic in the usual sense, but something modulated, encoded, perhaps even intentional. That possibility was too volatile for publication, so it lived in footnotes and encrypted email threads. A handful of researchers began calling it the Atlas residue, a poetic euphemism for a phenomenon no one wanted to name. They tried to model it, treating the signal as remnant ionization. The decay rate didn't fit, then they modelled it as scattered radio reflections from solar wind turbulence. Still wrong. The modulation pattern remained too clean, almost algorithmic, like a binary pulse decaying over time. When one of the researchers ran a Fourier transform on the combined data, an odd harmonic appeared, a repeating ratio of 3:2 across the peaks, the same resonance ratio seen in certain orbital systems, and in spacecraft telemetry beacons designed to distinguish artificial signals from noise. It wasn't proof, but it was enough to make people uncomfortable. At the same time, another oddity surfaced. The Parker Solar Probe, which had been measuring solar wind particles during that same period, recorded a minor disturbance roughly 2 days after 3I Atlas's perihelion event. The disturbance was tiny, a localized change in proton density, almost insignificant, but its direction matched the object's outbound vector. The plasma wave analysis team at NASA noted it in passing, labeling it non-repeating fluctuation of uncertain origin. No one connected it to 3I Atlas at the time. But when that data was revisited months later, the timestamp aligned almost perfectly with the first ALMA detection. The echo wasn't optical, it was electromagnetic, a ripple in the solar wind following the same path the object had taken. As evidence, it was circumstantial. As a pattern, it was undeniable. The signal, the magnetic alignment, the faint plasma ripple, all three shared one defining quality: order. Nature produces noise, but rarely produces coherence unless forced. Still, the team stayed cautious. Publicly, they called it coincidence. Privately, they kept watching. The last signal, if that's what it was, appeared in late December. After that, silence. Some claim the pattern had simply decayed below detectability. Others believed it had ended deliberately. One ALMA researcher phrased it best in a note that never left internal circulation. The emission didn't fade, it stopped. That distinction haunted those who noticed, because decay is natural, termination is not. Over the next months, the Atlas residue became something of a myth among the researchers who had seen the raw data. They spoke of it cautiously, in guarded tones, as though saying too much might invite ridicule or something worse. It wasn't a discovery, not officially. It was a ghost, one that seemed to hum faintly in the background of every new observation of the same region. Whether it was a trick of instruments, an artifact of human pattern recognition, or something left behind, no one could say. But no one could forget it either. And quietly, as the world returned to its ordinary rhythms and the public lost interest in what they were told was just another comet, a few scientists began to feel that something else had happened, something not visible in the light curves or the equations. They felt, though none would admit it out loud, that 3I Atlas had said something on its way out. Not with words, not with sound, but with rhythm. A whisper in the noise. A pattern just coherent enough to be recognized, just faint enough to be doubted. If it was a coincidence, it was the most articulate one ever recorded, and if it wasn't, then maybe, for the first time, the universe had spoken back. When the last echoes of 3I Atlas faded and the data stopped coming in, something shifted, not in the sky, but in science itself. The object was gone, but its fingerprints were everywhere, burned into equations that refused to balance. It had done something no comet, asteroid, or natural body should be capable of, and the numbers it left behind demanded to be reconciled with the laws that govern everything else. For a while, researchers tried to treat it like a technical glitch, a miscalibration, a coincidence. But deep down they all knew what that meant, rewriting part of the physics they had built their lives on. At first, the implications came quietly. A line in a report, a parameter that no longer fit. The acceleration curve violated Newtonian assumptions about conservation of momentum in an open system. The energy output didn't match the thermal input by an order of magnitude. The decay rate of the coma's brightness followed a curve that looked exponential, then flatlined. Every dataset whispered the same uncomfortable truth. Something had converted energy in a way that shouldn't exist. Something efficient beyond nature's habits. The first formal discussions happened at Caltech. A small group of astrophysicists, dynamicists, and plasma engineers met behind closed doors, the whiteboard filled with sketches of trajectories, equations, and fragments of theory that bordered on speculation. One idea was that 3i Atlas had demonstrated an unknown coupling between electromagnetic and gravitational fields, a kind of energy translation triggered by the Sun's magnetosphere. Another proposed it as a test case for radiative recoil, where photons from the Sun interacted with a surface engineered to amplify their push. That theory had once been used to explain Oumuamua's acceleration, but it failed here. 3i Atlas wasn't thin, wasn't reflective. It was dense, opaque, heavy. Radiation pressure would have slowed it down, not pushed it away. Then someone brought up something that silenced the room. What if the acceleration wasn't an effect, but an intention? Not an accident of physics, but the expression of control within physics. It wasn't a supernatural idea, just a reminder that physics doesn't forbid intelligence. It describes it. Every spacecraft we launch operates under the same laws. If nature follows equations, then so can something that learned to use them better. Still, no one wanted to write that down. The phrase artificial origin had already become radioactive, so they framed their discussions differently. Instead of saying engineered, they said non-thermal. Instead of propulsion, they said momentum exchange. Instead of control, they said feedback. Each substitution made the conversation sound safer, but everyone in the room understood what they were really talking about. One of the more daring proposals came from a theoretical physicist at MIT who specialized in thermodynamics of open systems. She argued that 3i Atlas could represent a new class of cosmic body, what she called energy equilibrators, objects capable of regulating their own thermal balance by redirecting absorbed energy into kinetic motion. Essentially, they would turn heat into movement with near-perfect efficiency. That idea bordered on science fiction, but it had mathematical support. The efficiency factor implied by 3i Atlas's acceleration was over 90%, something no natural process could achieve. If such conversion existed, it would force a re-evaluation of every model of energy transfer in the universe. It would blur the boundary between the living and the inanimate, because an object that can redirect energy purposefully isn't just reactive, it's adaptive. In Geneva, a group of researchers took it further. They began to speculate whether the laws of motion themselves could hide behaviours we hadn't noticed simply because we'd never seen them manifest. Maybe interstellar space, with its near-absolute cold and magnetic flux, allows matter to behave differently, closer to systems of feedback and resonance than simple cause and effect. They proposed that 3i Atlas had acted as a resonator, using the Sun's magnetic field to generate a temporary thrust through induction. It wasn't propulsion as we know it, it was physics finding a shortcut. Others disagreed. Induction could explain weak motion, not a sharp 90-minute impulse. To achieve that, the object would have needed to anticipate the exact configuration of solar fields, something even our own probes struggle to predict in real time. The calculations implied knowledge of conditions it could not have measured without foresight or memory. Theories began to collapse back into the forbidden question. How does an inanimate body act as if it knows? For months, debates spiraled without resolution. But through the noise, a few consistent themes emerged. The first was energy. The perihelion event had released kinetic energy far greater than any solar heating could produce. The second was precision. Every vector, every duration, every cutoff matched the optimization patterns of controlled systems. And the third, perhaps the most profound, was silence. No debris, no chaos, no inefficiency. Nature wastes. Whatever did this did not. That realization carried a quiet dread with it. If 3i Atlas was natural, then nature is capable of optimization beyond our understanding, meaning we live in a universe that builds order spontaneously, perhaps even intelligently without consciousness. But if it was artificial, then something else out there has already mastered those same efficiencies, and is using them not to announce itself, but simply to move, quietly, flawlessly, through the dark. Avi Loeb framed it differently in one of his lectures. Either we have underestimated physics, he said, or we have met its author. He meant it metaphorically, but the sentence spread through scientific circles like a spark. For the first time, the question of physics and purpose had merged. Could there be laws we've mistaken for accidents? Laws that only reveal themselves when something deliberately uses them? In an internal ESA report later that year, one anonymous scientist put it in simpler terms. 3 I/ATLAS may not have broken the laws of physics. It may have shown us the rest of them, that single line stripped of drama carried the weight of an entire paradigm shift. Because what if the universe doesn't lack intelligence? What if it is intelligence, expressed through structure, precision, and motion we haven't yet learned to interpret? The implications stretched further than anyone wanted to admit. If energy could be translated into motion with such efficiency, propulsion as humanity understands it would be obsolete. Interstellar travel would no longer depend on fuel but on resonance. If an object could use stars themselves as engines, harvesting their radiation not by brute force but by synchronization, it could cross galaxies without consumption, leaving no waste, no signal, no trace, just silence and movement. In that sense, 3I Atlas was less a threat than a revelation, a glimpse of what mastery of natural law might look like when stripped of arrogance and noise. Whether born of chemistry or craft, it had demonstrated something humanity had only theorized, that control doesn't always need power. Sometimes it only needs timing. When the last of the reports were filed, the scientists involved quietly dispersed back to their ordinary research, returning to the comfort of predictability. But the equations didn't leave them. In quiet moments, late at night, when the labs emptied and the screens dimmed, many found themselves staring at the numbers again, trying to see the meaning behind the precision. The object was gone, but its message was still there, carved into motion. And if the message had a translation, it might have been this: that physics itself is a language, and that somewhere out there, something fluent in it had just spoken first. By the start of 2027, the official data silence around 3I Atlas was deafening. There were no new press releases, no updates from NASA, ESA or JPL, no scheduled follow-ups in any major observatory calendar. The event had been quietly filed away, labelled as an anomaly, and left to drift out of the news cycle. But inside the scientific community, the silence didn't feel like closure. It felt like containment. Everyone knew the raw data existed: images, spectral readings, timing logs, telemetry, and everyone also knew that none of it had been made fully public. The phrasing "under extended monitoring," which appeared in NASA's final summary, became a kind of code among astronomers. It meant the event wasn't over. It meant someone, somewhere, was still watching. The question was, watching what? The last confirmed detection of 3I Atlas had come from a small research station in Hawaii in early January 2026. After that, the object fell below optical detectability, leaving only its modelled path, an equation extending into the dark. By that point, it was more than 6 astronomical units away, moving outward toward the edge of the solar system at over 200,000 kilometers per hour. No natural body had ever drawn such focused attention at such distance, except perhaps Voyager 1. Yet even with all our technology, it had slipped beyond reach as if it had simply turned invisible. Still, some people refused to let go. A group of independent astronomers, funded by private foundations and quietly supported by parts of the Galileo project, continued to point their instruments toward its predicted position. They weren't expecting visible light. They were looking for traces, echoes, any sign that the object was still active. Most nights they found nothing but static, but occasionally faintly they caught what they described as resonant interference, tiny fluctuations in background radiation that pulsed at frequencies too regular to dismiss, but too weak to analyze. The readings weren't consistent. They came and went like phantom heartbeats. When the group presented these results at a closed seminar in early 2027, the reactions were mixed. Some argued the signals were nothing more than calibration errors. Others felt differently. "We're seeing something coherent," one participant said. "It's faint, but it's there. If the object is inert, the pattern shouldn't exist. If it's alive or operational, it's whispering." The room fell quiet after that word. No one wanted to use it, but it hung there anyway. The larger agencies, for their part, avoided speculation entirely. Officially, the Atlas event was closed. In public archives, it was now categorized under cometary dynamics as an unexplained non-gravitational anomaly. In practice, that meant no one was authorized to speak about it, but no one was allowed to forget it either. Several new proposals for observation missions included a clause for rapid response to interstellar visitors. Funding increased. Telescopes were retasked to scan the ecliptic for fast-moving inbound objects. The hunt had resumed, but the tone was different now. Less curiosity, more anticipation. In March 2027, the Vera Rubin Observatory began its first full operational year, surveying the night sky in unprecedented detail. Within its first 3 months, it detected 6 new interstellar candidates. 6! Before Oumuamua, humanity had found 0. Before 3i Atlas, 1. The sudden jump in detections shocked even the most cautious scientists. Maybe our instruments had improved, or maybe something else had changed, something in the flow of space itself. The visitors were coming more often now, smaller, fainter, faster, each cutting through the solar system like silent messengers with no return address. Every one of them was logged, tracked and analysed. Most behaved as expected, straight, clean trajectories governed by gravity, but one, designated C/2027L3, didn't. It showed a faint deviation just past perihelion, small but familiar. The pattern wasn't exact, but it rhymed with 3i Atlas, a sudden, non-gravitational impulse, short and sharp, unaccompanied by visible jets. The deviation was minor, barely measurable, but it was there, and when Avi Loeb was asked about it in a brief interview, he smiled faintly and said, "Sometimes confirmation doesn't arrive all at once. It arrives like a knock that echoes." That quote circulated quietly, and within weeks, the comparisons began again. The orbital simulations placed C/2027L3 on a trajectory that would lead it toward the same general region of space, where both 3i Atlas and Oumuamua had disappeared. The same outbound corridor above the ecliptic. To the skeptics, it was coincidence. To everyone else, it was something closer to a pattern. By mid-year, the Galileo project had launched its own coordinated observation campaign. Their goal wasn't to prove intelligence or artificiality. It was to collect data before anyone could bury it. They developed an automated alert system to flag any new interstellar entry in real time, ensuring that every future visitor would be tracked from the moment of detection to the moment of departure. "We may not know what they are," Loeb said, "but this time we'll be watching the whole movie, not just the final frame." As months passed, hints of renewed activity surfaced. Deep space radio monitors began to record faint distortions in the direction of 3i Atlas's projected path, subtle warps in signal strength, almost like background interference modulating at intervals. It was weak, irregular, but unmistakably patterned. Once again, there was disagreement. Some called it solar interference, others a data artifact. But the few who had seen this kind of modulation before remembered the Atlas residue. Inside NASA's Jet Propulsion Laboratory, a handful of engineers ran trajectory updates using long baseline data. What they found was troubling. The object's position no longer aligned perfectly with the original exit projection. It had deviated, slightly but measurably. A course change. Again. The deviation was tiny, almost trivial, a few thousand kilometers off the modelled path. But it was enough to raise an impossible question. How could an object, supposedly inert and tumbling into the void, alter its course again, hundreds of millions of kilometers from any gravitational influence? The data wasn't conclusive yet. It needed verification. But within the closed network of astronomers who had followed the story since the beginning, the rumour spread fast. Atlas moved again. When that phrase appeared in internal memos, some scientists reacted with weary disbelief, others with quiet resignation. One message from a senior analyst at ESA captured the mood perfectly. "We are not discovering new physics. We are witnessing it publicly. There was still nothing." The agency stayed silent, waiting for confirmation. The word confirmation itself became sacred, a threshold no one dared cross without absolute proof. Yet proof in astronomy is a shifting horizon. The data comes first, the belief second, and the acceptance last. What made 3i Atlas different was that everyone already believed, even if they couldn't admit it. As spring turned to summer, whispers of a new joint mission began to circulate, a proposal to send a small probe toward the object's outbound path, not to intercept, but to observe from distance. It would be called Sentinel-1, a simple camera on a long ride outward, tasked with watching the darkness where 3i Atlas had vanished. Whether it would ever see anything was uncertain, but the symbolism mattered. Humanity had spent centuries watching the heavens for meaning. Now, for the first time, it was watching for movement. There were no new lights in the sky, no public discoveries, no dramatic revelations, just a quiet awareness that something had changed. The silence of 3i Atlas had become part of the background of human thought, a low hum behind every new discovery. It had moved once, then twice, and perhaps, even now, it was moving still. And as the last scheduled monitoring data for that year came in, one final note appeared in the JPL archives, unsigned and without timestamp. Object no longer observable. Residuals persist, awaiting confirmation. 3 words, that's all it said. But to those who had lived through the event, who had watched the sun flare and the trajectory bend, they were more than words. They were a pulse, a reminder, a question that hadn't stopped echoing. Because if the universe had indeed spoken through 3i Atlas, then maybe confirmation wasn't something to wait for at all. Maybe it had already arrived. The official records will say that 3i Atlas came and went, a visitor from beyond the stars, studied, debated, then forgotten. But those who watched it know better. They remember the silence before the shift, the moment the data bent, the feeling that something vast and deliberate had brushed past us. It wasn't spectacle that made it unforgettable. It was precision. It was the sense that, for a single night, the universe had stopped pretending to be random. We called it a comet because that's what our language allows. We said it was natural because that's what our science needs. But beneath those words is something older, the instinct that told ancient astronomers when to mark the heavens and when to fall silent. That same silence now surrounds 3i Atlas. It moved once, maybe twice, and then it left. Not toward us, but through us, carving a reminder into the space between belief and understanding. Perhaps it was just rock and ice obeying forgotten physics. Perhaps it was something built, guided, or aware. Either way, it forced us to see ourselves from the outside, a young civilization staring upward, realizing how little control it truly has over the sky it studies. 3. I Atlas didn't give us answers. It gave us direction. It showed that the unknown doesn't need to land on Earth to reach us. It only has to move with purpose, once, in the dark, and be noticed. Now it's gone, heading into the same quiet from which it came. But its trajectory isn't finished. It continues in equations, in late-night conversations, in the uneasy wonder of those who can't stop asking what it was. Maybe, somewhere ahead, it drifts toward another star, another civilization, another moment of recognition. Or maybe it simply keeps moving, silent, efficient, eternal, a line drawn through the void by something that understands motion better than we ever will. And if years from now, another light bends where it shouldn't, if another anomaly defies every model we build to contain it, maybe we'll remember. Maybe we'll understand that 3i Atlas wasn't the mystery. It was the message. The universe speaking once, clearly, through motion. A reminder that we were never alone in the dark, only unprepared to listen.